Carboxylic acid contains the carbonyl group and the hydroxyl group, and collectively they are termed as the carboxyl group. With these structures, we know that the hydrogen atom is protonic or electron deficient, and it has two oxygen with lone pair electrons that could be engaged in intermolecular hydrogen bonding. For physical properties, we have to take note that the polar carboxyl group is hydrophilic, while certainly the hydrocarbon chain is hydrophobic since they are non-polar. Let's now make a comparison between the hydrogen bond formed in carboxylic acid and that in alcohol. One of the key differences in carboxylic acid is that it has an electron withdrawing carboxyl group. The presence of the electron withdrawing carbonyl group would polarize the OH bond by actually shifting the electron cloud of oxygen towards C double bond O, and hydrogen, therefore, its own electron cloud will be shifted towards oxygen. So consequently, this hydrogen that you have here will be more delta plus than the hydrogen in alcohol, given the fact that the R group, which is an electron-releasing alkyl group, would shift its electron cloud towards oxygen, and hence in doing so, the electron cloud of hydrogen is less likely to be weighted towards oxygen. Therefore, because of this, when asked to discuss boiling point between carboxylic acid and alcohol, carboxylic acid tends to have a higher boiling point, assuming that both alcohol and carboxylic acid share the same number of electrons, because they form stronger hydrogen bonding, as the OH group is now more polarized, or the hydroxyl group is more polarized due to the presence of electron withdrawing carbonyl group, causing the hydrogen, specifically in the hydroxyl group, to be more positively induced. Next, we'll look at how the molecules could dimerize due to intermolecular hydrogen bond. You'll find that in the case of carboxylic acid, the carbonyl group could actually form a hydrogen bond with the hydroxyl group of another carboxylic acid, and consequently, you will find that both molecules could actually be binded together by two intermolecular H bond, as indicated here. So in the exam, you must be able to sketch and label them. When carboxylic acid dissolved in water, it's capable of forming intermolecular H bond, and certainly not just between the hydroxyl group and the water molecules. It could also be between the carbonyl group and the water molecules. So carboxylic acid is expected to be more soluble than alcohol, since it can form more extensive hydrogen bonds, because as far as alcohol is concerned, they do not have the carbonyl group. Chemical properties of carboxylic acid. In fact, only the reduction reaction is new. The rest of the others, you probably would have already learned it before. Let's take a look at the structure. From the structure of carboxylic acid, as mentioned, the delta plus is protonic and electron deficient, so the H plus could be donated, meaning to say carboxylic acid is an acid, as it's a proton donor. Next, carboxylic acid is able to undertake nucleophilic substitution, as the carbon in the carboxyl group is delta plus, and alcohol, which is a nucleophile, could actually attack the delta plus, resulting in the formation of ester. In nucleophilic substitution, the use of PCl5, SOCl2, and PCl3 would also enable the OH group in the carboxyl group to be replaced with a halogen. Finally, the last reaction is reduction. You'll find that carboxylic acid, as previously explained, is the most oxidized form, since it has the least number of hydrogen and the most number of oxygen relative to aldehyde and ketone and your alcohol. Alcohol, quick reminder, is the most reduced form, as it is saturated and has the highest numbers of hydrogen and the least number of oxygen. So when carboxylic acid is reduced, they will form primary alcohol. And we need a very strong reducing agent for that, and it will be lithium aluminum hydride. So in the case of the acid, as mentioned, carboxylic acid could now react with metal, it can react with alkaline, it can also react with carbonate as well as bicarbonate. In the formation of esterification, as previously recapped in alcohol, you will find that carboxylic acid would actually loses its OH group, while alcohol loses its H group to form the water molecules, and the process is actually reversible, and need sulfuric acid as a catalyst. Reflux is an essential condition. In the nucleophilic substitution of carboxylic acid to produce acid chloride, we could use either PCl3, PCl5, or SOCl2 as mentioned earlier. All have to be anhydrous, as all these compounds would actually hydrolyze or break down to other products in the presence of water. So a couple of examples to look at. So if you have reactions that have carboxylic acid and alcohol, then all the groups could in fact be replaced. So in this case, you need 4 moles of SOCl2. In this case, similarly, we have also 2 alcohol groups and 1 carboxylic acid group. So 3 PCl5 is required. In this example that we have an alcohol group and 2 carboxylic acid. So you need 3 moles of your SOCl2. Finally, in the case of this is not an alcohol group, it's a phenol. So nucleophilic substitution of phenol does not take place. So there's only an alcohol group. So you need 1 mole of PCl5. Finally, in the reduction of carboxylic acid, we have to bear in mind it can only take place in the presence of lithium aluminum hydride in dry ether. Lithium aluminum hydride is the strongest reducing agent relative to your NaBH4, sodium borotetrahydrate, and the other reducing agent is your hydrogen gas, which is too weak a reducing agent to reduce your carboxylic acid. So let's take a look at some examples. If you were to have 2 sets of carboxylic acid here, you obviously need to be able to reduce them. To reduce them, we'll need to have 8 hydrogen gas to be added, because for every 1 set of COOH, you will actually produce 1 water molecule. In the next example you look at, we only have 1 carboxylic acid, so 4H will be ample, and you get 1 mole of your H2O produced alongside your primary alcohol. So in this example, we have 1 carboxylic acid, we have 1 ketone and 1 aldehyde. If you can recap, your ketone will be reduced to form 2-degree alcohol, and your aldehyde reduced to form primary alcohol. Both of these will require 2H to be added, and your carboxylic acid will require 4H. So all in all, in total, we'll need 8H, and you can see that the primary alcohol, secondary alcohol, and your primary alcohol, as specifically drawn, has been produced. In the final example that we actually have 2 sets of ketone and 1 set of carboxylic acid. So in the same vein, 8H is required because your carboxylic acid requires 4 hydrogen, and the other 2 ketones respectively needs 2 hydrogen each. And so you're able to produce your primary alcohol. Both the other 2 alcohol produced from ketone are secondary alcohol. So finally, to recap, NaBH4 and hydrogen and nickel are not strong enough as a reducing agent to reduce carboxylic acid. We have to bear that in mind. And we also have to bear in mind that when we reduce aluminum hydride, you are not able to form aldehyde or to try and extract aldehyde en route when the reactions is going to end up as 1-degree alcohol. The reason is because lithium aluminum hydride is too strong a reducing agent. Therefore, it is only able to reduce carboxylic acid to actually primary alcohol. Hence, in the exam, if you're asked to produce aldehyde starting with carboxylic acid, you might have to reduce them to 1-degree alcohol and thereafter to oxidize it using acidified potassium dichromate and to undertake fractional distillation to extract the aldehyde. Finally, we want to wrap up reduction by mentioning that the ester, in fact, can be reduced. When you reduce ester, first thing that happens is that ester will break up to form your carboxylic acid and your alcohol. And thereafter, the carboxylic acid will undergo further reduction to give you primary alcohol alongside the other alcohol that was produced. In the reduction of acid chloride, what you get is that you will also produce primary alcohol, and the byproduct would actually be HCl. Finally, we also need to correct ourselves. When we first mentioned that carboxylic acid cannot be oxidized, there are some special cases where carboxylic acid can be oxidized. Let's highlight a couple of them. First of them is none other than your ethane diuretic acid. If you recap that in your when you first started the topic in redox titration, you was taught that the H2CO C2O4 could undertake reduction reactions as indicated here, and you were also asked to memorize the ethane diuretic ion can be easily oxidized. So one of the things that you remember, so your ethane diuretic acid could be easily oxidized to form carbon dioxide, and you're asked to remember and memorize this equation, and as well as the half equations for ethane diuretic, which when oxidized forms carbon dioxide. The next example we look at is none other than your methanoic acid. That's kind of like a fake carboxylic acid molecule. Why is that so? Because methanoic acid contains a carboxylic acid group. However, at the same time, it also contains an aldehyde group. So the aldehyde group can be easily oxidized by your potassium dichromate or your magnet, the traditional oxidizing agent. It could also, in fact, be oxidized by Toland's reagent as well as Fehling's reagent because of the presence of the aldehyde group.